So we have part 2 of the talk here. Hopefully most of you heard it last week. And so I assume you'll pick up from where you started last week. So if I might have a slight personal statement before you start. Hytham has been on the faculty how many years now? About 10?
12 years, man.
12 years. So he started and has been sort of a main resident of the controls group within the department, but in recent years has been doing a lot of work on the fluid side of things. So I guess once you need to teach more classes, then we can officially count you as part of our fluids group. But so he's tackled a lot of he's been looking into a lot of interesting fundamental aspects from the applied math side of fluid dynamics particularly. And sort of watching him transition from more of a controls to more of a fluids, I think he brings a nice, interesting, fresh perspective for us on a lot of the fundamental issues, recovering and remembering some of the very basics from Lighthill's vorticity generation mechanism, and we'll see more of it today, including some more recent developments on the applied math side.
Yes, exactly.
That I think are quite nice for us to review some of the fundamentals. So I think in that spirit, I hope you will enjoy today's talk.
Thank you so much. Thank you so much, Perry, for this super nice introduction. Welcome, folks, to part 2 of Changing Your Fluid Dynamics Religion, a testimony from a converted. So this is a recap of part 1. We just had a glimpse of the very rich history of the subject, and in my opinion, this historical account is not a luxury. It's not just it's nice to have it, because I think it's necessary to have the big picture and to recognize that the prevalent understanding that is currently taken for granted was once debatable between the biggest school of the time. And in fact, the winning school, the winning argument at the time was not the one that is currently prevalent. But second, and perhaps more importantly, is the fact that when you read the history and look at the current arguments of the proponents of the viscous school, you realize they are the same arguments. Ideal fluids cannot generate vorticity, cannot generate circulation, forces, D'Alembert paradox. They were stated before, and during the last 100 years, there were no new discoveries in the math or physics communities that add to these arguments. They are the same arguments, basically. On the other hand, there are some recent advances in the math and mathematical physics community that actually added some arguments that strengthened the point of view of the other school, and that's actually the topic of today. So we also, last time, what did happen? No? Yeah. What happened? Yeah, good, sorry. So last time, we read together some sections from Lighthill and Batchelor, and they made it clear that the vorticity generation mechanism is not done by viscosity. It's basically the body itself. The boundary condition is the main source of vorticity, right? And they invoked the no-slip boundary condition. So kind of concluded that it's not the viscosity as a quantity, as a quantitative effect. Its value is irrelevant. But qualitatively, it may be needed to enforce the no-slip boundary condition. That was basically, if you want to summarize their statements. But then came Morton and Terrington. Morton was a single paper. Terrington is a series of recent papers in the GFM. And they say, no, it's independent of viscosity, independent of the no-slip boundary condition. We read this together last time. The only mechanism by which vorticity may be generated on an interface is the inviscid relative acceleration due to pressure gradients of body forces. Viscous forces act to transfer circulation between the vortex sheet representing the interface slip and the fluid interior, but do not create vorticity on the interface. And they said it's independent of the no-slip boundary condition. So we need to investigate their arguments and touch upon their region of validity today. So last time we concluded by presenting this example. So I will do a recap for this example and continue. This is the impulsively started quit flow. So we have a stationary wall at the top. Do I have here? No, it's okay. because that's easy to that's difficult to control actually. Anyway, so you have a stationary wall at the top, you have a moving boundary at the bottom, which is impulsively started, and we're considering the so nice case, which is a laminar flow. So we have only one velocity component to the right, function only of y, so continuity is naturally satisfied, and Navier-Stokes reduces to the diffusion equation. So here viscosity, as you can see, is the sole acting force actually. So you just have viscosity and you have boundary conditions. So if it turns out in this extreme example where viscosity is the only player, right? If it turns out that the generation mechanism is independent of viscosity, then it's a crystal clear demonstration. So luckily in this case we have an analytical solution. You set your boundary conditions and initial conditions, and you do 200B or 230B. You can compute an analytical solution where lambda is an eigenvalue. Green terms are the steady state terms, and you have some transient, and we're focusing on vorticity, which is a function of y and time. So at a particular time, it's just a function of y. So a particular time, we have a curve here. Y-axis is the physical y. Horizontal axis is the normalized vorticity. And for any curve, it represents some moment in time. Blue is one of the early moments. Then you go in time, you get red, orange, purple, and then green, which is uniform. It's one all over. That's the steady state. So you said we can infer some conclusions from this figure. For example, you pick a curve, pick any moment in time, and ask where vorticity is maximum along the y. You will find that vorticity is maximum always at the surface. And then you pick the surface itself here and ask when vorticity is maximum, at what time. You find that the earlier the larger, so vorticity is really maximum at the beginning at time t equals 0, which is the moment of the impulsive start, the moment where the boundary condition changes. So at this particular moment at the surface, omega was infinite. It's a vortex sheet at the surface. And the conclusion of all this is that all vorticity is generated at the wall at time t equals 0. Why at time t equals 0? That's the moment again of the impulsive start. No further change of the boundary condition in the ensuing motion, so no further generation of vorticity. Vorticity is only and mainly due to changes in the boundary condition. So we then said, yeah, here is the channel. We can talk about, take an infinitesimal width here, delta x, and the whole channel height. So we can talk about, we can take this rectangular contour, right? So we can talk about the gamma of this contour. And the gamma of this contour simply represents the total amount of generated vorticity inside. And since things are uniform in x here, you can simply divide by x to get what we call circulation distribution, which is simply the total amount of generated vorticity in the slice, all right? You can see easily that this is from the analytical solution. You plug the transient solution here and you get this that is independent of time and independent of viscosity. Independent of time, why? Because all the generated vorticity was generated at time t equals 0. No further generation happened. So it's the total amount of vorticity is conserved. If you change, like Professor Semiano mentioned last time, if you play with the boundary condition, you will have this as a function of time, but it will always remain as independent of viscosity, right? Always independent of viscosity. So another example, which is similar in nature and spirit, the impulsively started rotating cylinder in a quiescent flow. So similarly, we consider this the easy and laminar case. We have only tangential flow velocity u that is function of r only. So this automatically satisfies continuity, and Navier-Stokes then reduces to the diffusion equation. Again, viscosity is the only acting force. There is no convective term. And you can have an analytical solution. That's the steady state terms plus some very lengthy expressions for the transient. But it's the same conclusions. At any moment in time, omega is maximum at the wall. At the wall, omega is maximum at the start. And at the start, at the wall, omega was infinite, a vortex sheet. So all this conclude that all vorticity is generated at the wall at time t equals 0. And if you take a global measure, we're always interested in the global measure. The local events may depend on viscosity. We're talking about the global measure. Everything was happening in the flow. So the total vorticity inside the domain from R to infinity 0 to 2 pi, you plug this analytical solution into here and carry out some integration, and it comes out constant, independent of time, independent of viscosity. All right? Mustafa?
There is a typo here, like the vorticity is equal to 0, is that right?
No, it's not a typo. The steady state, yeah, that's so interesting. And this is one of the interesting examples. Basically, you have a finite amount of vorticity and distributed over an infinite domain. So now every little part takes a measure 0. So the steady state is 0. The steady state is a potential flow, is an irrotational flow. A good point. So from all these, they really concluded that the vorticity generation mechanism, we can talk about the semantics here, but the viscosity has nothing to do with the generation itself, the generation of vorticity. And indeed, they are talking about the total, if we want to be precise, it's the total amount of vorticity. And this is a mathematical proof. I mean, it's not, it's not debatable. The total amount of vorticity in the domain is independent of the value of viscosity. That's a universal fact.
But
Which is,
you need a sticky fluid.
well, we will come to it. And maybe perhaps to have a reconciliation, I'd like to make this distinction. There is a fundamental difference between vorticity as the curl, the rotationality of a fluid element. You have a fluid element and you hold it, and when it's rotating, that's the little omega. That's the curl of it, right? Versus gamma, which is a global measure of omega, right, in a thin layer, which in the limit it actually takes the form of a jump of tangential velocity, like a vortex sheet, basically. They are fundamentally different in the sense that this animal, it needs viscosity. A fluid element, to rotate an incompressible flow, you need viscosity. This does not need viscosity. That's perfectly fine in an inviscid fluid, the jump of a tangential velocity. But what was the source of this rotationality of the fluid element? Where did the fluid element get its rotationality? From the neighboring fluid element. And where did this neighboring fluid element get its rotationality? From the neighbor. And then what is the main source? It was from the body itself as gamma. So this gamma is the source of that omega. I know it's confusing, but this gamma is inviscid, that omega is viscous, but this gamma is the source of that omega. Anyway, if this means anything to you. Let's go back to Professor Serignano's point. Do you need stickiness? Do you need the no-slip boundary condition? So this, perhaps when you read it in the textbooks and the papers, I think it's a bit convincing. But I think the argument now is, fine, it's not the quantity of viscosity, but it's the quality of viscosity. Because we need viscosity to ensure the no-slip boundary conditions. In all these examples, we ensure the no-slip boundary condition. Right? So let's see. So this was tackled actually in Turrington. That's the main schematic diagram in their paper. They have fluid interaction, and they said you can also apply the same tools, and I'm going to talk about this particular point later. You can apply the same thing with fluid-solid interaction and take viscosity to infinity. But for now, let's consider fluid-fluid interaction, and there is an interface between the two fluids. So they define the total circulation of the outer contour, which is simply the total vorticity in fluid 1, total vorticity in fluid 2, and the jump across the interface, right? And now they did a very interesting derivation. I think that's the main contribution of the paper. They used Navier Stokes, incompressibility, and the no penetration boundary condition to derive a closed form expression for d gamma by dt. That's equation 222 in the paper. And it came independent of the tangential boundary condition. Basically, they did not need the tangential boundary condition to get the total amount of generated circulation in this fluid-fluid interaction. So basically, let's demonstrate it by examples. So if you have a no-slip here, the tangential boundary condition, let's force it to be no-slip. What happens? No-slip means that the two flows here, the two tangential flows, they should not move relative to each other, right? So there is no jump, basically. So gamma is 0. So all the already generated vorticity here must go into the fluid. How? By viscous diffusion. So you really need viscosity to enforce the no-slip boundary condition on the interface, correct? Now you can consider another tangential boundary condition like free surface, which is 0 shear stress. Now the already generated vorticity here, some of it will remain on the interface and the rest will diffuse into the fluid. How much is needed? It depends on the boundary condition itself. And again, the mechanism that takes the already generated vorticity into the fluid is viscosity. So you need viscosity to ensure either form of the tangential boundary condition. But if you don't have any tangential boundary condition and you don't have a means or mechanism to take vorticity and unlock it from the interface into the fluid interior, then all the already generated vorticity must stay on the interface. And in the three cases, the total amount of generated vorticity and circulation is the same. It's independent of the tangential boundary condition. And this is just math.
When you say boundary condition, are you talking about the condition in the middle of the flow?
Yes, and the interface.
Okay.
So the total amount of vorticity, yeah.
It's a condition on the contact surface.
Yes, yes.
We can get into a semantics discussion about whether it's a boundary condition, but I won't go there.
It's okay. Yeah, it's okay. But I mean, this is their main derivation. The total amount of generated vorticity in a fluid-fluid interface is independent of viscosity and independent of the tangential boundary. It's not only the no-slip, it's whatever tangential boundary condition you have here is irrelevant. All right, so that was,
But
yeah.
when you, coming back to this, when you take domain A1 or A2, and you integrate the vorticity over the two-dimensional domain, you are accounting for, let's say you take A2, you're accounting for the velocity along C2. And when you take A1, you're accounting for the velocity along C1.
the tangential velocity on C2 and C1 here come from Euler solver. That's the
But
point.
The vorticity, the Stokes theorem will tell you that the vorticity in domain A1, for example, has to go all the way around C1, right?
Yeah, yeah,
To
sure,
get
sure.
velocity.
Yes, yes.
And if I get the Stokes theorem on A2, I go around A2. So embedded there are the velocities along C1 and C2. C1 prime and C2 prime.
These come from the
They're embedded in that calculation of the first two integrals.
This comes from the inviscid flow solution. When you solve the inviscid Euler here, you get naturally a tangential boundary condition. So you get something like this.
Okay, well,
You
what
get
I'm saying-
and this.
All I'm saying is the velocity along C1 prime and C2 prime are implicitly contained in those two integrals by Stokes' theorem.
And then
So I would argue your tangential condition on the contact surface is implied.
no. That's the important point, and that's no. When you solve pure Euler here, you get naturally a tangential velocity here, the same there, and this difference is the source of the vorticity in the domain. This is independent of whatever boundary condition you
I'm
put.
not saying it isn't.
Yeah, so
I'm just saying that the conditions for that contact surface are implied through the two integrals.
I don't know exactly what does this mean, or
I think he's saying that the sum here is independent of the tangential boundary condition.
yes.
But how it's distributed amongst the two components.
Yeah. I mean, and this is valid all over the talk. We are talking about global effects, right? And the generation.
All right.
So the generated amount of the total, that's the total. This is the total. I mean, we're not making any other claims about the local distribution. The total is independent of viscosity and independent of the no-slip boundary condition or any other boundary condition. It does not need stickiness for this particular example. So that's a big jump, but it was surprising to me at least.
Well, you could have it slipping. on that contact surface.
Yes, exactly.
Oh, fair enough.
Yeah, good. So we're on the same page. So actually, Professor Johnson, during conversation, he actually made a very interesting point. He said, yeah, you can, in a fluid-fluid interface, this is acceptable. Because what I just exactly said. I mean, you can solve Euler here, solve Euler there. You get tangential velocity here and there. And this slip is the source of the vortex sheet from which viscosity will consume and take into the fluid interior. But if you have, in our interesting case in engineering, where fluid and solid, now, let's say this is the solid, I will not be able to solve Euler here, right? And my only means to know any information about this is through the no-slip boundary condition, which is fair enough. So I said, yeah, I mean, let me think more about this case, right? I mean, a fluid and solid. And we know from last time, I mean, the writings of Lighthill and Batchelor is that, okay, you solve first the inviscid flow dynamics, you get the tangential velocity, what we call U edge, right, which we think as the edge of the boundary layer, which is really the main source of vortex sheet, which upon, when you enable viscosity, it just smears this out into a layer of finite thickness for high Reynolds number. But as we know that the total amount of generated vorticity is dictated by UE, and let me stress here before moving any further, UE is independent of viscosity quantitatively and qualitatively. This coming from a pure Euler solver, right? Actually, this statement, when I thought about it more, is not precise. If we want to write it mathematically precisely, this should be not UE. It's UE minus the surface velocity. So it was written as if US is 0, right? So you really need US as the no slip from the no slip boundary condition here, kinda, right? In this picture. Then I said, okay, let me now make it more specific on my interest, the example that I'm always interested in. So this part of the wall, this surface, is a part of a body immersed in a fluid, and it's moving with an arbitrarily moving velocity. So US is the tangential component of U, all right? And at any moment in time, we can write down the circulation as the integral of vorticity inside the boundary layer. Now we know from here that the inner integral over y is simply UE minus US. And US is just the tangential component of U, so it's U dotted with dx. If U is not varying over the body, which is represents a very common case in aeronautical engineering, mechanical engineering, so we have this. And now we're integrating dx over a closed contour. That's 0 irrespective of the tangential component here. And indeed, the circulation is mainly and solely dictated by the inviscid flow dynamics quantitatively and qualitatively. You don't need stickiness. So now we have, in the case of fluid interface, total amount of generated vorticity is independent of viscosity, quantitatively and qualitatively. And in this also special case, which is very common. Can there be other cases where this is not valid? Perhaps yes, if you have a rotating cylinder. Maybe in that case, we absolutely need the viscosity and no slip. I'm not debating there or not arguing. I really need to study that case in detail. But for this case, which represents this is a very common case in engineering. No, circulation is an inviscid quantity, which is very interesting by itself. So are you trying to say that if we just numerically solve Euler, we will get circulation and lift? Yes, indeed. If you go here and... I'm sorry?
Questions?
Oh, yeah, sure.
So a couple points more on the math side, maybe not.
Please. No, go ahead. Yeah.
Of interest applications. One, you're assuming I didn't install a conveyor belt on the surface to give it a different tangential velocity. But two, when I integrate from 0 to delta, if I have a delta function of vorticity at the surface, it's sort of mathematically ill-defined. So are you integrating from 0 minus, slightly below the interface, or 0 plus, slightly above the interface?
I'm saying that this is a viscous fluid, so there is a boundary layer, and inside the boundary layer, the solution is smooth. So this integral is well defined. So I'm saying that even in a viscous fluid, where you apply no slip and do all this, it turns out that the total amount, this computation is assuming a viscous flow, turns out that the generated gamma at the end is dictated by what was there from the purely inviscid flow dynamics. It doesn't need, if I now ignore all this and say, okay, what is the inviscid flow solution of this? There is a u edge tangential to the body. What is the circulation? Is the integral of u edge. It's exactly this, so they match each other. So if you do an integration of a smooth solution of Navier-Stokes versus the straightforward circulation when you get an Euler solution, they are exactly the same.
So what's the point about the role of no slip here then? Because you have a no slip condition.
That's what I'm saying, is that this, for this particular case,
Yeah.
which is very generic, the no slip plays no role in the generation of circulation. That's exactly the point.
I'm not sure.
Well, you get the same circulation
Yes?
if you pick the right Euler solution. You have
Yeah.
an infinity of Euler.
Yeah, we're coming back to this. Yes,
Okay.
yes, yes.
So,
yes, yes.
all right.
Yeah,
So
we're coming
one
back
of-
to this.
One of an infinite
I
number
didn't get that either.
gives you the right answer.
You say no slip, there's no rule.
But
In-
you're enforcing
yep,
no slip.
yep.
You have a no slip.
No, just 1 second. We agree first, what is UE? UE is the pure Euler solution without no slip and without viscosity. Do we agree about this? If this is the case, then these are the computations saying that the total circulation in the viscous flow is coming from this. This is exactly the circulation in the purely inviscid flow. They are exactly the same. The no slip comes here, it doesn't matter. As long as you, that is, Professor Johnson made a very interesting point, which is if you have a conveyor belt, I don't know, maybe this will not hold. But for this particular case, which is very generic in industry, if you have a body that is immersed in a fluid and moving with arbitrarily time-varying velocity, this amount of generated circulation is independent of viscosity quantitatively and qualitatively, which is it was surprising to me. And the analysis is so simple. It's not, but
You didn't draw an Euler solution.
what is that?
You drew a viscous solution that satisfies.
No. Let's go back. At the beginning, we said, let's go back to Lighthill and Batchelor. What they said is that at time t equals 0 and an impulsive start, go and solve your pure Euler solution. You will get a tangential velocity distribution on the surface, right?
Okay.
And they said,
So you have a velocity jump there.
there is a velocity jump, right?
Okay.
There is a velocity jump, and if you allow viscosity to take over, you will get this, right?
Okay.
You will get that the total amount of generated vorticity locally at some station will depend on UE minus US. And then I said, okay, let me now look at the global quantity, because that's what I'm interested in. If you look at the global quantity, it turns out that the effect of this US goes away. And you have the contribution from the pure Euler solver only. That's the point. Which actually is not, I mean, it may be surprising if you come from some angle, but it's not surprising at all if you're coming from the angle of Morton and Terrington and all these recent developments. It's not basically saying anything new other than what they just said already in the GFM papers in 2020, 2022. I cannot publish this work. It's already known now by them, not by me. So that's what I'm trying to say. In fact, yeah.
Sorry, interrupted.
No, no.
The green integral goes over where?
The green integral said
Yeah, the green integral
this over the body.
over the entire body.
Yeah. It's the total. I'm interested in the total effects, total circulation, total vorticity inside the boundary layer inside the body. I mean, over the body.
So what's the role of the no slip condition? Are you saying?
I'm
that
saying
no
here.
role?
I'm saying here exactly. I'm saying here like this particular case.
Hmm.
A fluid interface, there was no role whatsoever of the tangential boundary condition. I'm saying the same for this particular, which is interesting case to us as aeronautical engineers. I'm saying there is no role whatsoever of the no slip boundary condition.
Then if I want to calculate distribution of circulation around therefore, okay, so all I have to do is, I don't need to know the vorticity everywhere. All I need to do is take a contour that's in the potential region and just go around it. I think
That's it.
basically what you said.
That's all it's saying.
This is exactly that.
Yeah.
Yeah, that's
So
exactly
that-
it. So I'm saying the viscous solution, the circulation from the viscous solution turns out to be the same.
Okay, so if you go back to your A1 and A2, if you took if there's no vorticity in those domains, but only at the contact surface, If you integrate it separately over the perimeter of A2 and the perimeter of A1, you would get zero circulation for each.
That's
But
right.
if you take the parameter globally, C1 and C2 without C1 prime and C2 prime, you would get a circulation.
Yeah, that's why they have here.
Yeah, you would get a circulation.
Yeah.
And I think
Good.
what you're saying
Good.
on the following slides is essentially equivalent to.
Yes, I'm not.
Okay.
It's global effects are independent of viscosity, independent of the no-slip boundary condition. Again, there might be exceptions, and maybe many exceptions to these cases. But as far as what I just shown here, which were surprising to me when I learned it the first time, this is the case.
But it's not surprising, because otherwise we
That's
would
good.
never use potential theory.
That's good. That's good. That's good. That's good. If it's not surprising, I'm very happy that it's not surprising.
No, but am I missing something? It's possible I'm missing something.
Yeah, good. That's
You agree?
very good. That's very good. I'm-
Okay.
You're
Please.
implying that UE is independent of viscosity.
Independent of viscosity.
Then we get into the Kuta condition.
Yes. That's exactly my next slide. So the question coming from here, are you implying that if you numerically solve Euler, we'll just get left in circulation and everything? Kshitij?
I have a question that the initial solution that we get from the implicit one, how crucial is the impulsive start to that solution?
The impulsives, it doesn't matter. You can do it continuously, and if you're doing it in a numerical simulation fashion, delta t by delta t, each delta t is considered as an impulsive start. There is a mathematical proof for that, as long as you're doing it continuously. Yes, please,
You
Perry.
should continue, but continue with my objection that you didn't demonstrate that the no-slip condition doesn't play a role here.
Say it again.
You should
No, you tell me what.
So go back, your initial slide showed a vortex sheet at the surface. Okay.
Yes.
No,
Here.
There's a vortex sheet at the surface.
Yes,
So what's the integral from 0 to delta of omega at this initial point?
I'm saying this
No,
is
no, go
no,
back.
just one second. I'm
See,
saying
here you've
this
already
is
applied
this
the
is the
no-slip
viscous.
condition.
Yes.
You've already applied the no-slip condition here. Go back.
Here
to
is the
beginning.
no-slip condition. That's the no-slip condition. Yes, I'm applying the no-slip condition to get a circulation that is from a viscous solution. It turns out that the effect of US cancel out, and you just are left with the inviscid quantity.
But initially, did you have, go back to the end. So here you have the integral from 0 to delta of omega dy. There, clearly it's non-zero, right? Go back to your initial drawing. What's the value here?
Value of what?
Integral from 0 to delta
It's
of omega
it's
dy.
UE minus US. Yeah, I showed here. It's UE minus
So you're
US.
integrating from 0 minus, slightly below the interface.
Integrating what?
So, because the initial vorticity distribution is a delta function. at the
It's
interface.
delta function, but
So
it
how
has
do you
a
integrate a delta function from 0 to delta if the delta function is on the boundary? This is mathematically opaque.
yes. So a delta
You
function.
have to say whether you're slightly below the interface.
A
or
delta
slightly
function. When you're saying a delta, I think you don't mean this delta, right?
No.
Yeah.
I mean a Dirac delta. function.
Excellent. A Dirac delta
Do
function.
you agree that's
Yeah,
a
yeah.
Dirac delta?
No. Yeah, that's a Dirac delta function. A Dirac delta function, by definition, is actually it doesn't make sense. It's a distribution. Doesn't make sense only when you integrate it. So the integral, you don't need to go minus epsilon plus epsilon. No. It's that definition in the entire domain, from 0 to infinity of this.
But if I place a
It gives
Dirac
you
delta-
this.
If I place a Dirac delta exactly at the limit, that's mathematically not. what
No,
it
that's
is.
the precise definition of the Dirac delta. A Dirac delta at a line, that's the precise
No,
definition
it has
of.
to be within the integral. If you put it on the boundary,
No.
it's not well defined.
No. Yeah, I mean, you can. I mean, I'm not negating. Let me.
Doesn't have to be a Gaussian. Doesn't have to be
No, a
symmetric.
delta function.
Let me. Instead of going into semantics, let me just be clear. Forget about the vortex sheet. We're talking about purely viscous solution.
Yeah.
So purely viscous solution, there is no vortex sheet. There is this picture. Do you agree about this picture?
Yeah.
Good. Now we go and integrate over the entire boundary layer.
Yes.
What we get is this. What is this? Now, if I ignore the viscous solution completely and go and solve Euler, I will get UE over the body and get the circulation over the body. That's exactly the same. So I'm saying that if you want to get circulation from the viscous solution of Navier-Stokes or from Euler, they are exactly the same. That's what I'm saying. Yeah. So there may be some semantics here and there, but But I think the demonstration is clear. This amount of generated circulation of that particular example, which covers a wide class of problems in aeronautics and race cars, wind turbines, is independent of viscosity and independent of the no-slip boundary condition. It doesn't need stickiness.
If you choose the right
Wait,
order.
please continue under,
Yes.
Under my objection.
Okay, yeah, of course. I mean, that's okay.
We have to do something about that. He's acting like me.
So, no, it's. I mean, I like this. It's very healthy, and I really like it. That's I spend years and years with these, and they were surprising to me. So I'm very glad that it's not surprising. So it's the question here is, like I said, if we numerically solve Euler, will we get circulation and lift and drag, and because that's against the intuition. Let's look. This is Hirsch, a CFD book, one of the interesting books, and let's read together. This is volume 2 and section 19.4. Let's read together. It appeared that computations based on the Euler equations and which did not implement any form of Cotta condition still produced accurate results of circulation. These are unsteady simulations. This has been confirmed since then by many computations on 2-dimensional as well as 3-dimensional airfoils and wings. They just simulate Euler, they get lift and circulation, accurate prediction, this is unsteady flow, just fine. And they added, this remarkable result implies the existence of some mechanism, there must be some mechanism, which reproduces and simulates the essential physical phenomena leading to the generation of circulation and lift. Why they are saying remarkable, and there must be some mechanism, because again, that's the preoccupation of the idea of viscosity is the master, and it's the reason behind this. So when you get it without it, you feel like there is something here, right? There is something. Let's pause for like 10 seconds, try to imagine what kind of mechanism that could have come to their mind.
What are they imposing on the Euler equation?
No slip boundary condition.
No?
No slip. There is free slip. It's Euler, just Euler.
But then,
Unsteady though, unsteady.
that's your answer.
No, it's a big difference.
You still need to impose.
I'll tell you why it's a big difference, because when you do it in a steady fashion, there are the issue of infinitely many solutions that you talked about. But when you do it in the unsteady, your numerical solver will capture the stable solution only. The other solutions do not matter.
If you specify for a given initial conditions.
Yeah, always. That's any linear, nonlinear dynamical system. It depends on the initial conditions. That's always the case. Has nothing to do with non-uniqueness.
Okay.
So that's...
Are you going to talk more about that?
Of course, yeah, that's it's a whole thing. I mean, the mechanism that they suggested is because of the preoccupation of viscosity is following. They said, well, what are you actually simulating with Euler? If you go and simulate Euler for a non-trivial problem, it will blow up. It will not give you these nice results of the non-lifting solution where the flow goes around the sharp. It will never happen. It may blow up. It may blow up. Most likely it will blow up. So what they had to do to stabilize their numerical computations, they added numerical dissipation, right, to the algorithm. So they said, well, it's that numerical dissipation that plays the role of artificial viscosity. Because, we cannot live without viscosity, so there must be some viscosity in there, and it's really this artificial or numerical dissipation. They're
arguing in favor of viscosity.
What's that? No, I'm presenting what is there in the
No,
literature.
but I mean, what are they saying? Are they saying
They are saying
that
this
some kind of
mechanism.
viscosity is important?
Yeah, I mean,
Some kind of dissipation is important.
well, no, just one second. So when they removed viscosity, simulated Euler blows up. When they added numerical dissipation, all right, to the algorithm, they got lift and every circulation fine. So they interpreted these results that, what allowed the enabling mechanism, what allowed them to get the right solution is the numerical dissipation. There is one caveat here though. Again, there is no slip boundary condition. There is no boundary layer. There is no boundary layer in these simulations. So that's very interesting. Even if you're adding, if you're adding just viscosity without no slip boundary condition, what are you gonna do? There is no slip boundary condition here.
Then, so the viscosity enforces Kuta condition.
Yes, so that's their interpretation, is that the numerical dissipation played the role of viscosity. That's their interpretation. We're gonna come back to it, all right?
But the numerical viscosity was not focused on a boundary layer, apparently.
No,
It was
no.
focused on regions of high velocity.
Yeah. Which will manipulate the solution. I'm not denying that.
Be larger, closer to the air. Is this for an airfoil?
It's an airfoil, yes,
Yes.
wing and 3-dimension,
So
2-dimension.
the numerical dissipation will be largest as you get closer to the airfoil.
Yeah.
And it starts to approach a boundary layer, if not precisely a boundary.
It did not cause a boundary layer, because a boundary layer need to match the no slip boundary condition.
I understand, it's not a boundary layer, but it's a neighborhood layer where the
Yeah.
velocity derivatives are larger.
Good.
You're getting closer to the physics.
Yeah, but there is no
So it's
slip.
not surprising.
It's not. Nothing is surprising at all.
Okay.
I mean, it was surprising to me when I was learning, but I'm not saying that this will be surprising to anyone.
Being modest.
No. So then came Hoffman, and we invited Hoffman here in the summer to give a talk, but I really wish that he talked about this, but he didn't. Probably it was too controversial to ruin his summer vacation. But anyway, so he wrote, or they wrote, we find by computational solution of the Euler equations with slip boundary condition, there is no enforcement of the no slip, that the potential solution develops into a turbulent solution with substantial drag and lift. We thus obtain, without any presence of viscous boundary layers, substantial drag and lift in accordance with observations and the conjecture of Birkhoff. Later, in particular, we show in these references that the drag and lift of a car and an airplane can be accurately predicted by computing turbulent solutions of the Euler equations with slip boundary conditions without resolving thin boundary layers. This is by fluid dynamics expertise considered to be impossible.
So these are unsteady.
Unsteady simulations.
So in order to do the impulse start, are we changing the boundary at the free stream velocity, or
it feeds your problem through.
flow, and then we assume a different,
Most likely these simulations, I'm not sure. Most likely these simulations they start with zero everywhere. Zero everywhere, and
at every time step a different infinite boundary.
the no penetration boundary condition is your means to know what's going on. So you have U infinity, so U infinity sine alpha gives you the no penetration. Go ahead.
That's not terribly surprising. is it?
At
Because
all,
for
yes.
For turbulent flows, we use things like law of the wall. We never say no slip bar. Well, I won't
Good,
never say.
that's good.
If you go to DNS, you do, but
I'm really happy. I'm not arguing.
But you're
Did they resolve skin
you're
friction?
basically dissipating.
No. That's a very good point. No skin friction. No skin
So how
friction.
can they claim airplane drag and
Because at very high Reynolds numbers, in they got pressure drag. They got pressure drag.
well, that's only a fraction of the total, right?
No, for three-dimensional wing, no, it's actually for two-dimensional foil at very small angle of attack maybe, but for three-dimensional wing, no, it's significant, right? I mean, that's induced drag, and induced drag is actually you get it from Prandtl lifting line theory, fine. So it's not surprising that Euler can get it to you, right?
Yeah, at optimal conditions, induced drag is half of the total drag.
At the optimal conditions, yes, that's right.
The other half is
They don't get skin friction drag. Yes, they don't get skin friction drag. Yeah.
That's
Yeah.
the problem.
Yeah, that's, of course, this is a problem. But remember, the original debate was what? There is no way viscosity is necessary. You need it as an enabling mechanism. You need stickiness, right? No, there is no such a thing. You can get lift. They may be, by the way, the lift and drag here may be wrong. I don't care. But you don't need, it proves that viscosity is not an enabling mechanism. That's the main point, all right? That's the main point. It's not an enabling mechanism. You can live without it. In many applications, not Like Hoffman, when he came here, he said, I'm not trying to remove viscosity from fluid mechanics. That's an expressive statement. That's a good one. Yes, of course, we should not think that viscosity, we should not go all the way in the pendulum, right? From viscosity is super important and the main god to viscosity is not important at all. No. No, but we should be, realizing that there are some phenomena that you can get perfectly fine without viscosity, like lift, for example, and circulation. Skin friction drag, no. All right, pressure drag, yes. So we need, and maybe under some conditions, not in general. So we need just to be, I need to be careful, and we all need to be careful with these statements as we go. So that was the last straw, right? That artificial viscosity is necessary. You didn't completely get rid of viscosity. You need even the slightest of it in your numerical code. What are you going to do about it? So we'll come back to this in the talk, but in order to go and discuss the nature of artificial viscosity and whether it's really viscous or really artificial, we're going to discuss this towards the end of the talk. But to do that, we need some background. I think what could be a good reconciliation between the two schools is that when we view these solutions as inviscid limit, it's as if you're solving Navier-Stokes with viscosity and no slip boundary condition and taking viscosity to zero, gradually. Then you eventually reach a limit. So this problem really is mathematically, intimately related to this open problem mathematics convergence of Navier-Stokes to Euler. You have here nu n is viscosity and half sub n because we're going to talk about sequence of viscosity. So you take viscosity like 1 and then 0.1, 0.01, 10 to the power negative 10, 10 to the power negative 16, a sequence of viscosity converging to 0. At each value of viscosity, nu n, you're going to pray that we can solve Navier-Stokes equation and the corresponding solution is un, right? On the other hand, here is Euler, no viscosity. The solution is denoted by u sub 0. And the open question in mathematics is, as this sequence of viscosity goes to 0, does the sequence of viscous solutions of Navier-Stokes converge to that of Euler, all right? And that's open problem mathematics. What do you mean by open problem? There is no single counter example, and if you have it, you will be a very big shot in math tomorrow morning, all right? There is no counter example. There is no single situation where we have viscous solutions converge to a flow field that is not a solution of Euler. And let me talk about this because it's a bit, misleading. First of all, on the outset, this may seem to be a fancy math problem, fancy abstract math problem. And indeed it is. I mean, it's occupying the minds of the best mathematicians of the time, field medalists and all over the place. But it has very practical considerations, very practical consequences on many industries. Because in these industries, airplanes, race cars, submarines, wind turbines, you name it, engineers in these industries, they perform in their routine everyday tasks numerical simulations of Navier-Stokes, and these industries, the operating Green's number is very high, 10 million and above, right? So there is no supercomputer on the planet that can perform a single numerical simulation of Navier-Stokes for these examples. So we are in a bad need for approximate solutions of Navier-Stokes at high Reynolds numbers, all right, that come from, first principles, not ad hoc like industry is doing nowadays, like crayons, for example. So if this convergence holds, it will imply that the solutions at the infinite Reynolds number, at strictly infinite Reynolds number, may serve as a good approximation of the solutions at a very high Reynolds number. The difference will be order epsilon. All right, so if this convergence happens, and if we have a way to pick up the limit, I mean, there are many open questions. And when you present this to a fluid mechanics student, sometimes the initial response is, what open problem you're talking about? Here is an easy counter example. Here is the flow over a cylinder where we know that at very high Reynolds number, the flow separates, creating some behind. Whereas when we solve Euler, all the solutions we know they are attached flow solutions. Right, so none of these can approximate. They are very far in any norm. So here is a counter example, right? And in fact, it's not only this counter example. When you look at Euler equation, it enjoys energy conservation, circulation conservation, vorticity conservation, helicity conservation. So this is why some fluid mechanicians, they may look down at Euler equation. It's not interesting. It's not producing, turbulent dissipation. Energy is conserved. It's not producing lift and circulation. It's not producing vorticity. It's a nice equation to have, but it's not rich enough. And that's true for only classical or smooth solutions that we are aware of. If you look here at the candidate counter example, what's happening in reality here? In a Navier-Stokes solution, I have a thin layer at very high Reynolds number. I have a shear layer. Here I should have a shear layer. And the thickness of this shear layer shrinks as Reynolds number goes higher and higher, right? So in the limit, as the Reynolds number goes to infinity, we expect that the limiting solution will have a zero thickness of the shear layer, i.e. a sheet of discontinuity. So the solution, the limit that we are expecting is actually discontinuous, right? Is discontinuous. So it cannot be understood as a smooth solution of Euler. Now, if you open the space to allow for discontinuous solutions, none of these conservation laws hold. None of them. So you may have a purely Euler solution that is dissipative, doesn't conserve energy and generating circulation and so on and so. So let me talk about this. So how we understand these solutions, the discontinuous solutions. Let's take a deep breath because I like this simple example. It was revealing to myself when I made it up the first time. Please.
When you say the layer will go to zero thickness, you're still implying laminar flow, right? Not turbulent flow.
No, even turbulent flow.
Turbulent shear layer will not go to zero thickness.
Well, it will. If you have a laminar flow here, and this after a while the transition point is downstream of the shear layer, you can have turbulence here, and this is the case, and the thickness goes to zero.
So you're looking very locally, very near the cylinder.
Yeah.
You don't care what happens.
No, you care what happens. That's okay. You care what happens, but I'm saying that if we are to capture a true Euler solution that represents physics here, we should expect a discontinuous solution. We should not expect a smooth solution. If we restrict ourselves to smooth solutions, it's as if we're searching in the wrong space. That's what I'm trying to say.
So in the emissive limit, the Komogorov scale will go to zero. And actually, I mean, there's a lot of mathematically debatable things in terms of finite time singularities and things like this. But I mean, the Komogorov scale will go to zero in the emissive limit. So you'll have similar challenges.
But if you have vortex sheets, you cannot predict the physical cascade known as turbulence.
Say that again?
If you try to predict the physical cascade that we know as turbulence, well, you keep on going down to smaller scales. I don't believe you can do that if you're taking discontinuities to vortex sheets. I've never seen that done.
No, actually, this is a very interesting point. I have a hidden slide for it, but I don't want to disturb this. But in fact, when they did, let me, the quick answer to this. In fact, that's happening in reality, even with a Navier-Stokes solver. If you go and do Navier-Stokes simulations, very high Reynolds numbers, and take this and try to locally to see the flow structure and to analyze how smooth or rough is the solution, they are almost all of the solutions. They are almost nowhere differentiable. They are not smooth solutions.
You get vortex stretching and vortex.
You get vortex stretching, and with what?
With sheets, zero thickness sheets.
No, I didn't say that. So maybe I misunderstood your point. What is your point?
You're talking about. I may have misunderstood your answer, but I thought you were saying your vortex sheet model can predict turbulence.
The vortex sheet model is very well known to roll up into a spiral.
Yeah,
That's
not turbulence.
that's
It
okay.
may be
Yeah, if you have
unstable, unstable, but
yeah, if you have tons of them,
no,
The-
but I don't think it'll predict the cascade process.
that's
Smaller and smaller scales and vortex stretching and all
that's
that.
that's
I think you need a continuous fluid.
no, this is what I'm saying, is that this one, so now regarding to this, the continuity of the fluid, or actually the smoothness of the flow.
I'm not saying
No.
you won't get instability, but you won't get what we know as turbulence, I suppose.
The turbulent flow solutions are not smooth, all right, in the numerical sense. They are not smooth. I mean, I can show you some papers at the end.
For DNS, they are.
No, that's what, I mean, I can show you some papers at the end. I can show you some, these are not the point. I'll
Defense professor, I'll go about you.
okay.
He's more stubborn than me.
Very quick question.
Please.
So when you say the solution is not differentiable anywhere, it has come out from a numerical solution, right? So is like the interpolated solution not differentiable, or?
That's a good question. I need to go to that paper and look back at it. So this is just to get, this is a cartoon just to give you an what do I really mean. This is an algebraic equation 1D. It's so simple right now. This is just elementary school stuff. And if we ask how many solutions do we have for this equation? Well, if you are really pre-1500, where you only learn about real numbers, you never heard about complex numbers, you will say with full confidence that this equation has only one solution. But if you're, in our time and you learn about complex numbers, then you say, yeah, we know that this equation has 3 solutions. So the main lesson that I'm trying to say here is that once you open the space of solutions over which you're doing your search, more solutions may emerge. This is in general in any problem, all right? And maybe one or some of these newly emerged solutions, they may be more physical than the original ones. That's what I'm trying to say. The same for an ODE or a PDE. If we are before the 1940s era, then our focus on these equations are only on smooth functions. Why smooth functions? Because if I want to say the problem statement here is that find a function u such that when you evaluate it at a y multiplied by sine, and evaluate the derivative at the same y multiplied by y, you get 0. So this means that you need to have a derivative that is defined everywhere. So the function needs to be smooth and differentiable. So if my physics are telling me that the expected solution, the expected physical solution is discontinuous, it cannot be understood in the classical sense. You need to come up with a new notion of a solution. That's the notion of weak solution that allows discontinuities. I had here like 3. So this actually came out after the Schwartz came up with the theory of generalized functions, distributions, so allowing weak solutions here that do not require differentiability of the function. I have here some demonstration, but I'll have to run because I'm really out of time. Wow, I have some interesting stuff that I need to say, and I'm out of time. So the concept of weak solutions of Euler and how rich they are, it was tackled in many papers by Greg Eying. Really, it's amazing, beautiful work over the last couple of decades, which was culminated in a 70-page GFM paper last year in GFM Perspectives. I'll not talk much about this, but let me summarize some of his statements. Let's read together. It may be less commonly, It may be less commonly appreciated that singular or weak solutions of Euler, incompressible Euler, are a good candidate to describe turbulent flows in the asymptotic limit as Jones number goes to infinity, as first conjecture by Onsager. He's a mathematician, and this is what he's writing. Who's Onsager? Onsager was a Nobel laureate and a chemist. He was interested in fluid mechanics at some point in his career. He produced one paper in fluid mechanics in which he wrote, turbulent dissipation could take place without viscosity In the absence of viscosity, the standard proof of the conservation of energy does not apply because the velocity field does not remain differentiable. And this was very well known to the math community, perhaps much less known to the fluid mechanics community. So when I learned this, this was shocking to me. What is the source of dissipation in oil? You don't have viscosity. Are you saying that Euler, pure Euler, not the implicit limit, pure Euler, is dissipative on its own? That's what they're talking about. So this was a conjecture. This was very well known. The conjecture was about the following. What is the minimum level of smoothness below which Euler is no longer guaranteed to be conservative? Onsager conjecture said, he conjectured that if the flow velocity is Holder continuous with exponent less than 1/3, then energy conservation is no longer guaranteed. So what is Holder continuity? It's a measure between continuity and differentiability. To give you an example, the purple function is x squared, smooth and differentiable everywhere. The yellow function is absolute value of x. It's not differentiable here, but the derivative is bounded everywhere, all right? So this is a Holder continuous with exponent 1. Call it Lipschitz. This is square root x, the red. So it has exponent half. This is exponent 1/4, and so on. So this just gives you an idea what are we talking about here, all right? So this was in the 40s. And then the math community did amazing effort building on the legacy of John Nash, and they constructed crazy solutions, weak solutions of Euler and Navier-Stokes. So very recently, 2018, a rigorous mathematical proof of Onsager's conjecture, which means give me an initial solution that is rough enough. I let it evolve under Euler dynamics in the weak sense, and in finite time, the solution becomes the zero function everywhere. The initial kinetic energy, the entire initial kinetic energy has completely dissipated in a purely Euler solution, not an invested limit, strictly zero viscosity. So that was very interesting to me.
Oh, are you talking about u being x to the n power?
Yes.
Why is it going down to 0?
Going down to 0, what do you mean?
At x equals 0. Over here.
X or to the 1/3, kinda.
So it's going in, but it's not going infinitely, right?
Yeah, I mean, these solutions are understood in the L2 sense, which means you cannot talk about one particular point. You can remove whatever point you don't like, okay? There are lots of math behind this. It's not that easy to grasp. But anyway, it's a legitimate weak solution of Euler. It may not be physical. That's
No, I just don't understand what you mean by x to the n.
x to the n.
Is it, that's what
No, no,
u
there
x
is.
to the n? What
It's easy. There is a very precise mathematical definition of Holder continuity with exponent 1/3. And the theorem simply says if you're in this region, energy is no longer conserved. That's the theorem.
You're not saying u equals x to the n.
It goes by delta u, it goes by, so the changes in u, it goes by the changes in x to this n. Yes.
Changes in x. Okay.
I gave examples here, Bill, right? So these are the examples.
Oh, so these are derivatives that are non-traditional.
These just to give you the idea, what do you mean by 1/3? So 1/3 will be between the red and the blue here.
So you're saying instead of differentiating u with respect to x, you're differentiating with x with respect to x at some power?
No, there is no derivative. U may not be differentiable. If n is less than 1, it means that you may have points in the domain where u is not differentiable.
I guess I'm confused about the relationship between u and n, but maybe you can tell me.
Delta u goes by delta x to the power n, kinda, roughly.
So in the limit, the u equals the x.
Exactly,
power
the
n.
limit does not exist. You're exactly
So
right.
that is traditional derivative.
Yes, exactly. You're exactly right.
Sorry?
Fractional derivative.
Yeah.
No, you're exactly right. The derivative does not exist. Yeah, they are not differentiable. That's the issue. Yeah. All right. So Eink actually showed a similar limit on, for Kelvin circulation theorem. In a recent paper, Eink, he wrote, the drag on the body in the infinite Reynolds number limit can be computed entirely from the limiting weak Euler solution. without the need to resolve small viscous length at the wall. I think we can summarize with this. In one of Ein's paper, he said, under very modest assumptions, the viscous Navier-Stokes solution must tend in the limit to a weak solution of the incompressible Euler equation. I think all this, if we're going to take a take-home message, at least to myself, I had more respect to Euler equations after I read this than before, when I was treating Euler as a, something that does not produce rich flow behaviors. Indeed, it can produce very rich flow behaviors, dissipative, and circulation generating, lift generating, and so on. So I'd like to go back, maybe 5 minutes, just to, because this is actually interesting about the artificial viscosity. Remember that was the last straw in the argument. So if you have Navier-Stokes and want to simulate it, but on a relatively larger size grid, we're not doing DNS. We're doing LES or RANS, which covers almost 100% of the cases in industry and many cases in academia. What do we do? Well, then Navier-Stokes, you cannot solve it as is, right? You need to add the unit stress, right? Because you're not resolving down to the Kolmogorov length scale. But what is the source of this term? Why we're adding it here? Well, this term really, if we're doing LES, so this term coming from filtration of the nonlinear term, right? Has nothing to do with molecular viscosity. In fact, if this is not there and you're talking about Stokes equation and you do LES filtration, you will not have this term. So we pick up this term, it appears only because of the nonlinear term, has nothing to do with viscosity, right? And then one of the standard models of Reynolds stress is the eddy viscosity. Oops, sorry about that. The eddy viscosity model, right? So you immediately realize that this is not a good name. The topic was already controversial, and we want to really see which is viscous and which is not. And now we know that this has nothing to do with viscosity, and you're calling it eddy viscosity. It has nothing to do with viscosity. Indeed, the action of eddy viscosity is not viscous. That's to begin with, all right? But here is the point. If this term is there because of the nonlinear term, and we're doing a relatively large mesh size, but this term exists in Euler. So if you're doing Euler, why don't you have this term also? I think that's the main new point, at least to me, or because of Onsaga's conjecture. Because in the past, we thought that Euler is not dissipative. The main contribution of this term is to provide dissipation, all right? So when we think that Euler is not dissipative, we don't think to add this term when we do Euler on a finite size mesh. But now after we realize that Euler has intrinsic dissipation, if we want to be faithful to the Euler dynamics, we need to add a model for the Reynolds stress. When we can do LES with Euler, or even if we do, we need to model the Reynolds stress if we do pure Euler simulation. That's an important point. Another relevant important point, in Navier-Stokes, there is a scale. If you went down to it, you don't need to add this term, which is the Kolmogorov length scale. In Euler, there is no such a scale. Any finite resolution, you will have to add this. This is unavoidable. This is important. All right? This is necessary if you want to do proper simulations of Euler. I think that's perhaps the new part when it comes to numerical simulation. So now let's connect it to implicit LES. What is implicit LES? Implicit LES is an approach where you said, since the main contribution of this is to give you dissipation, I'm going to ignore it and have my numerical algorithm to provide dissipation, numerical dissipation, all right? And there is debate in the community over the last, let's say, 10, 20 years, whatever. Should we do implicit LES, no subgrid scale model, and the numerical solver provides dissipation, versus explicit LES, where my numerical solver is conservative and I have a model, explicit model for the Reynolds stress, right? I don't care about this debate, but let's here, make it clear that there is some equivalence between having a Reynolds stress model and numerical dissipation. Because adding to it or wedding it to the fact that if you're doing Euler, you need this term, this implies that the artificial viscosity is perfectly legitimate. Because what is artificial viscosity? Artificial viscosity was a numerical dissipation added to an Euler code. So It's an implicit LES, actually, that is replacing the effect of a subgrid scale model that was necessary because of the filtration of the nonlinear term to give you the right dissipation of Euler that is intrinsic to Euler dynamics. Indeed, the artificial viscosity is neither artificial nor viscous. That's one of the main points that I wanted to make, and perhaps I'm going to copy this here. So that's the energy spectrum. This is wave number, right? So it's the reciprocal of the length scale. So large scales will come here to the left. We all know that this is inertial range, this is viscous dissipation, this is Kolmogorov length scale. And please, this is a cartoon, so don't pick upon it. When we do a resolution that is much larger to the Kolmogorov length scale, that's my delta x, and this is the resolvable range. We don't see any dissipation coming from molecular viscosity. So this is why in the very recent paper, very interesting paper by Finn, they wrote for a finite spatial resolution at very high Reynolds number, molecular dissipation through the viscous term is impossible. You will not see it because the small scales relevant for molecular dissipation are not resolvable. Hence, the Euler equations are actually the mathematical model seen by the numerical discretization scheme. It's like you think you're solving Navier-Stokes, you're actually solving Euler, kinda. So it's, do I have time? Oh, wow, my goodness. So I will have to probably, unfortunately, this was interesting from Prandtl, but there is no time, but I will have to stop. And I'm sure that this lecture was far from addressing all questions. It actually, I'm sure that it raised more questions than it answered. I actually came all this when I was curious to understand a very simple problem in aerodynamics, how lift is generated on a two-dimensional airfoil. Basically, when I was doing our variational theory of lift, the variational theory of lift itself, it raised more questions than it answered. In fact, I was discussing with Scott Bolt, Syrian Caltech from Muri Garib Guru. He came here and gave a seminar. We had numerous discussions, and in one of the email exchanges, he sent me, I know a professor at Cornell who privately told me that they are very happy that you opened up this can of worms. So it's like this, right? So you're all over the place. There are tons of things that from weak solutions to Onsager conjecture to, to circulation and lift to D'Alembert. It's a very rich topic. The conclusions here is that I think we agree that the vorticity generation mechanism at an interface is inviscid and independent of the no-slip boundary condition. Proper CFD simulations of Euler equations without no-slip, they are very rich already and resulting in lift and drag and separation. These solutions should be viewed as inviscid limit of Navier-Stokes. On the other hand, the weak solutions of Euler, they are also very rich. They can be turbulent and dissipative, lift generating, and so and so. But here is, in my opinion, here is really one of the $1 million questions. The weak solutions of Euler, they are infinitely many. They are not unique. So if we have a selection criterion that can pick from this family the inviscid limit, that would be amazing. And this is why, in our group, we're very interested in the principle of minimum potential, pressure gradient as a promising selection criterion that can hopefully pick this unique solution from the family. Of course, I thank my group. Tons of discussions and debates in the group about these concepts. Support from the funding agencies, and thank you for attending.
Can I just make one comment?
Please.
About the name of anti-viscosity?
Yes, please.
It comes from nonlinear term. The history goes back to Reynolds stress K-epsilon model. So when you have Navier-Stokes equation and you do time averaging, you will end up term like UI, usually a little fluctuation, correlation between two components of fluctuating velocity. And the people, this is 1970, what do you do? That represents some stress. And since the laminar stress is called mu du dy, take ui uj and call it turbulent stress, and then
But you need a viscosity,
Yes.
and it's called turbulent viscosity.
Yes.
The name goes back
Yeah, yeah.
to the Reynolds average.
Yes, 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 yeah, yeah. Thank you so much, Dr. Yeah.
You want to go
It's-
back to 1970?
Yeah.
I thought it was earlier.
It's Mustafa, yeah.
I wasn't looking.
About KF, 1970.
It's
Boussinesq was actually the first one.
I think, yeah, Boussinesq.
Boussinesq was the first one to
Right, but I'm
propose
just talking
an
about-
effective viscosity.
I know, but yeah,
I don't know if you call it an eddy viscosity.
right.
I-
I'm talking
I-
about the name
Yeah.
kinetic viscosity,
Yeah.
K epsilon derivation.
Yeah, to me, the name in the light of this debate is a bit confusing, frankly speaking. Mustafa, you have a question?
Actually, I have two questions.
Yes, please.
So the first question is, can you explain again why Euler solution is deceptive? I didn't get that.
I think you need to take a course in applied mathematics.
Yeah.
Take 10 weeks to.
Okay.
It's not easy, but okay, I'll say this way, and take it and go and try to check it yourself. You go and try to prove the other way around. Let's not take things for granted, and let's try to prove that Euler is conservative. You go on step by step, and it's a very easy proof, like half a page or 3-4 lines. You go and step by step, you will find yourself in the middle writing down the gradient Naplayu. You're relying that the Naplayu exists. We are doing it without thinking about it because but when mathematicians do it, I mean, they cannot try it Naplayu unless they are sure that it exists. So if the velocity field is not differentiable, Naplayu does not exist, and your proof no longer holds. And that was Onsager's conjecture. That was the main motivation behind Onsager's conjecture.
You mentioned that dissipation comes from numerics. So that is
No. That's a very good point. Intrinsically, Euler dynamics, these solutions, I mean, in the math community, they were made a splash in the math community. They were analytical solutions, no numerics, and they purely dissipative, all right? Oh, yeah. No, that was a big deal in the math community. It's really a big deal. It's the finest mathematicians of the world, The point is, so Euler intrinsically has its own dissipation. Now, if we're going to numerically simulate it at a finite resolution, we need to represent this dissipation. You need to either add a Reynolds stress model, or you do a numerical dissipation.
The second question,
Implicit LES, yeah.
the second question is, do you think Navier-Stokes equation is right? Yeah, I mean,
What do you mean? What do you mean, right?
The viscous stresses, maybe the viscous stresses, this is not the right form for the viscous stresses.
No, I'll change the question a little bit if you allow me, please.
Yeah.
Because people would say the following: well, there is this whole mess about Euler. Let's just ignore it and focus on Navier-Stokes. It's nice and fine. I think what I'm trying to say here is that I didn't discuss it in this lecture, but it's not nice and fine. In fact, it has similar issues. If you go to compressible flows, for example, compressible Navier-Stokes, it is known to develop singularities in finite time because you have shocks, all right? So develop singularities in finite time. After the singularity, what you're going to do? The classical solution is no longer valid, and you have to talk the language of weak solutions. You say, fine, I'm going to have weak solutions for Navier-Stokes. They are also non-unique. They are non-unique, and we need a selection criterion. That's why the question of a selection criterion is really a big one. Please.
I would like to build on Mustafa's question. So, in the last talk, we talked about Navier's formulation coming out of a molecular hypothesis. Have people looked into the viscosity model from a molecular hypothesis? Because most of the textbooks that I have read until now, they start with the
Continuum.
relative velocity formulation. We ignore the higher order terms, assuming that the continued derivative of relative velocity is continuous with respect to spatial distribution, and then further on we go to make assumptions about isotropy. So now my question is, like, if I were a controls person who looked at a system, nonlinear system, gave it an input and gave it an output, how can I characterize, like, for example, if there were a certain solution of like 10 meters per second versus 100 meters per second, and it was the same fluid with certain viscosity, how can I be sure on a molecular level that the response to both kinds of impulsive starts is going to be like similar? Maybe it's not possible to have a solution in the incompressible range, and there will be a break-off at the molecular level.
It could be. So first of all, you mentioned Navier argument. I'm not aware of anyone who picked up the Navier. In fact, it's not available in textbooks or in papers. You find it only in history, which is interesting. I think it deserves, it's a high risk effort, but I think it deserves someone to look at it and, remove the dust and see what we can get out of Navier's stuff. Back to your question about the incompressibility. Like I said, so at least the incompressible Navier-Stokes 3D is an open problem. The compressible Navier-Stokes is already known to have singularities in finite time. We already have issues there, all right? So at least there is a hope in the incompressible, because we know that incompressible 2D, we don't have singularities. We don't have singularities. There is a global solution. That's the Ledizhenskaya, celebrated proof. We have solutions in 2D. 3D, it's an open problem. Compressible, it's already known that we develop singularities in finite time. You need to make, let me show you this because it's interesting. Yes, so look at this. Look at this. This paper came out 2025. Interpreting convex integration. Convex integration, that's the mathematical tool developed by John Nash and others. And this is the main mathematical tool the mathematicians, the pure math analysts, which we do not understand their work, they use to develop these crazy solutions. Look at this theorem, came out in 2019 on Navier-Stokes. We're talking about Navier-Stokes with viscosity and no slip and everything, all right? But it's weak solutions. Let's read the theorem. It's just half a minute. It's so easy. Look how bizarre it is. It says, give me any arbitrary energy function, all right, that is defined on some interval. I guarantee that there exists a weak solution of Navier-Stokes defined over the same interval such that the energy of the Navier-Stokes solution is given by this function. So what is bizarre in it? What is bizarre in it is this can be this is arbitrary function, arbitrary. It can be growing in time. It's not necessarily dissipative. So give me any crazy energy function, I can construct a solution of Navier-Stokes, not Euler, that matches this energy. It's like, come on, man, this is too much. This is why in that paper they were really saying, folks, we really need, even for Navier-Stokes, a selection criterion to single out the physical solutions from the non-physical solutions. That's the real challenge.
The energy function is assumed to be bounded over this time interval.
Yes, I think this should be. Let's assume that it's bounded. Let's assume that it's bounded. Anyway, it's a compact set. So I would say that it's bounded, but it can be growing with time. Mustafa.
I just want to go back to my question. The viscous stresses. Do you think it matters if it's Newtonian or not? Like, is there a proof that, like, the form of the viscous stresses?
I think if you relax the Newtonian assumption and had other models, there are existence and uniqueness, and life is happy there.
This is the only problem with the Newtonian assumption.
Let's say it's a problem with the Newtonian assumption. It's one of the problems with the Newtonian assumption, yes.
That means that it's not right.
These are big questions I will not be able to answer. It's you're talking about Navier-Stokes. Anyway, yeah, thank you so much, folks. Mark, maybe a last question?
So we're assuming that there's one solution that Navier-Stokes is converging to, and the Euler, which is an Euler solution, and you wish to pick one. Would it be so bad if there were two solutions and both are valid? Like, both are.
You know from sequences, if there is a limit, it has to be unique. If there is a limit.
Well,
So-
there
so-
could be two limits. I mean, you could have a sup limit and the other one, the bottom limit.
No, but that wouldn't be a limit.
It could
Right?
be an oscillatory
But
limit.
this is not a limit, right?
But the
That's
sup limit can exist and then the.
yeah. So you can have a sequence that oscillates, fine, at infinity, but that's not a limit. A limit is limits of sequences are unique. But I think so. Let me say something. So these are two questions interrelated. They are not one. Do solutions of Navier-Stokes converge to begin with? Second, if they converge, is the limit a solution of Euler? There are two questions. All right.
Is there any physical principle that would prevent two solutions from forming? You have some
It's an open problem. I don't know. People, I think that physical principle would be the selection criterion that they are looking for. It's so Professor Sirnian was alluding to something related to entropy minimization. That's a very interesting concept, but how to bring it to the forefront of the mathematics world, it's challenging.
That's often a selection criteria, right? It can be used.
It's but it's not enough with Navier Stokes. It's not sufficient.
always enough.
Yeah.
Sometimes.
Sometimes yes. Second law of thermodynamics. All right. Thank you so much, folks. Thank you. Shittish. Thank you, Dr. Said. Oh, thank you so much. Thank you for the comment, the historical comment. I like the history. So
Yeah, you should really.
thank you.
You should really tell people that no longer. Oh, about the you're talking about the stress.
Yes.
Oh no, I thought about the
Yeah.